Hi. This lecture is about sampling distributions, the whole sampling process mathematically, and estimation. It's complex, and the mathematics in it gets really complex. But I want to give you my point of this is to give you an introduction to it, to have some sense of what it's about. The good news is there won't be a lot of points associated with this week. So if you get confused, have a hard time with it, it shouldn't have a lot of impact on your grade. But I want you to have some sense about how this works and why we do this. There are a couple of key concepts that we're going to come back to here. One is I'm going to come back, I'm going to reintroduce a different kind of distribution this week, and there's a sampling distribution. Now, we've seen distributions before, and just a couple of weeks ago, we talked about the Z distribution for a standard normal distribution. We're going to come back to that tonight, but with a different sort of variation around that. The other thing I want to mention is some stuff about talking about samples and populations. That's a concept you've heard before, but here's a place where it starts becoming really important, is to think about samples and populations and being clear about what you're dealing with those things. So let me do a fair amount of screen sharing tonight. I've got a number of things to talk to you about here. Key piece here, come back to is with a sample, we have a mean, well, both samples and populations, we have means and standard deviations. When we're talking about the mean of a sample, we use the X bar. We talk about the mean of a population, we use mu, the Greek letter. We use standard deviation, they'll use S or SD more commonly. For the population, we use the Greek letter sigma. Typically, these are called, for samples are called statistics, for populations are called parameters. Why do we do this? A key part of estimation, of inferential statistics, is that what we want to do is we have data from a sample, and what we want to do is we want to infer something about a population given the data we have from some smaller sample. We can't go out and talk to everybody in the world and know what everybody in the world thinks, and note down what everybody in the world thinks about something. We can pull a sample, and if we do it well, we do a good sampling process, we can infer information about the population from our sample. Now there are all sorts of caveats with this, and I'm going to introduce some of my caveats along the way as we go through it. Let me start off by just noting a sampling distribution. This is a different kind of distribution. You've seen binomial distributions, you've seen frequency distributions, you've seen probability distribution. A sampling distribution is a theoretical distribution of a sample statistic. We're up here. It's one of these things here: mean, proportion, or standard deviation from an infinite number of samples from a given population. Now I'm going to come back to my point is it's a theoretical distribution because nobody does an infinite number of samples, but we can mathematically make some judgments about that. And there are things about that we can know from this. We work from the assumption that if we have done a reasonable sampling procedure so that we don't have a biased sample, if we went back and did this again and again and again, there always would be some variation within the sample. The numbers would never come out exactly the same just because you got different people doing stuff. But if you're pulling different samples, an infinite number of samples from a population, over time what's going to happen is you start going to get some stability about the mean, for instance, the proportion that what you're working with. Some characteristics of a sampling distribution. A sampling distribution will tend towards being a standard normal distribution as n gets larger, above 30. when you have small sample sizes, 15, 10, 12, what tends to happen is just because you do stuff randomly, you can end up with some really unusual random events. I mean, if I was doing a random sample of for a political poll, it is possible that I could pull a sample of 10 people from the state of Vermont. And of those 10 people, I might end up with 5 Black, gay, elderly men. It's not likely. In fact, it's fairly unlikely, but it is possible that that could happen. And if I'm doing a survey on attitudes about something or other, that could radically bias my outcome. If 5 of the 10 people in my sample were elderly, Black, gay men, that would bias my sample towards that. I don't know what the attitudes of that group is, but would not be a representative of the state of Vermont, at least. On the other hand, I mean, that's with 10 people. If I said, oh, let me do something larger, and instead I had a sample of 100 people, but I still got the same 5 men that I'm talking about here. And instead of being half my sample, at that point, it'd be 5% of my sample. It would have much less impact on the overall population because the sample size has gotten larger. If, on the other hand, I had 500 people in my sample and the same 5 men that were saying, leave me alone, stop surveying me. These 5 Black, elderly, gay men would be 1% of the sample, in which case it would have very little impact on the overall bias in biasing the sample. So as the sample size gets larger, what it does is it levels off the differences and ways that the potential unusualness of some of your selection might be. So sample size becomes a really important issue. Since you're doing an infinite number of samples, the mean of a sampling distribution of sample means, say X bars, will be the population mean. Now, how do we know this? Mathematically, I can prove it. It could be proven. I'm not going to try and do that tonight. The mathematics of it is a little complex, but trust me on this. The mean of a sampling distribution is the mean of the population. As the samples, if you do an infinite number of samples, the mean of the sampling distribution becomes the mean of the population. And similarly, if I was doing proportions, the mean of a sampling distribution of sample proportions would be the population proportion. Let me give you an example of that, for instance. I do a sample of folks on gender, and assuming that we could get answers that were that simple dichotomous male or female, which is an interesting question at this point, but just as making that assumption for simplicity's sake, I might get a sample where I would have 80% females and 20% males. Well, if I were doing that, for instance, of NVU students, I think that's high. But if I did it an infinite number of times I sampled from it, the mean of the sampling distribution would come out with which should be equal to the proportion that they are in the overall population, which is all NVU students. Now, that's a conceptual point here. It's like, I will say, come back to this more here. In a sampling distribution, the standard error of measurement is the standard deviation. And the standard error of measurement is equal to sigma divided by the square root of n. N is the size of your sample. Sigma is the population standard deviation. So the standard error of measurement is the population standard deviation, not your sample standard deviation, population standard deviation divided by the square root of n. As n gets larger, that number gets smaller. As n gets smaller, that the denominator here gets bigger, and so the standard error of measurement is bigger. And the standard error of measurement is the standard deviation of a sampling distribution. Now, you're saying, huh, Steve, what does that mean? I'll come back to this. It's an important point, Howard. I'm trying to do some definition of terms here, just to give you a sense of this. Let me go to my bead box here and see if I can pull this off. What I'm going to do is I'm going to stop sharing. I'm going to see if I can take my camera here. Get to see my jade tree. I've had that jade for almost 50 years at this point, getting close to 50 years. It's an old jade tree. Over here, let's see if I can get a picture. This is a bead box. And the bead box has in it red and blue and white and yellow and green and brown beads. And there are 1,000 beads in the bead box. I don't know if I actually counted them, but I don't think I've lost it along the way. If I asked you, what's the proportion of green beads and brown beads? Now let's say red beads and green beads. And I take a paddle. I've got a paddle here that has 25 holes in it. And I stick the sucker in, and I get a sample. And my sample has 23 white beads and 2 green beads. So I've got 0 reds and 2 greens with a sample of 25 things in it. Keeping this as independent, I'm going to replace those. And reach over here and say, come on, let's see if I can get this up a little bit more. Okay. Now I have a paddle that has 50 things in it. This one, there are some yellow ones here, but for you, they look like the white ones. The yellow ones probably look pretty much the same. There's 1 red and 3 green and 1 brown. So you get a different kind of a picture of what's in here because the sample size has basically the sample size doubled in this piece. Now, the question is, which one of those things would you prefer to have as if you were looking for something here? Well, I have one more thing to do. Switching hands. This is kind of a clumsy process. Okay, now I've got 100 things here. So our first one had a sample size of 25. Second one had a sample size of 50. Third one has a sample size of 100. And here I have a bunch of yellows and whites that you can't tell the difference probably because in this light I can barely tell the difference. I got 1, 2, 3, 4, 5 greens and 1 brown. The sample size makes a tremendous amount of difference in terms of what you pull up, in terms of how well it tells you what you've got. What the sample size does is it determines the standard deviation of a sampling distribution. We just had 3 samples. Now they're different size samples, granted, but you got to think about if you're going to be sampling from this box, this bead box, which one would you prefer to have? The answer obviously is the 100 one. Makes a whole lot more sense. With the 25, you would have said there's no reds in this thing at all. With the 100, you see 2 reds. So it suggests to you that about 2% of the beads in this thing, 2% would be about 20 out of 1,000, might be the proportion that you would have. That's an estimate. It's an estimate based on a sample process. The theory behind the sampling distribution is I might take my 50 box thing here, so my 100, and I just do it an infinite number of times. I'd keep doing it and do it. Now, realistically, you would get something different each time with it. You would never get the exact, well, you might occasionally get the same thing, but you probably get something slightly different each time. But over time, what would happen is you start saying, okay, the proportion of reds here actually comes out about 25 out of 1,000, or 22 out of 1,000. You know, you start getting a sense of, it's like, oh, there's starting to be some stability in the numbers I'm getting here in this process. And the same with the greens. You start saying, oh, okay, I had 1, 2, 3, 4, 5 greens this last one, 5 out of 100, so about 5% greens. Multiple samples over time gives you a converging picture on where the center of that distribution is. And that's the whole point of a sample distribution. It's a theoretical distribution. Nobody does an infinite number of samples, but we can infer some things from this, and the math will back it up essentially. So what we're trying to do is we use sampling distributions to help us infer things. Estimation is the simplest type of inferential statistics. There are other kinds of inferential statistics. You can look at the differences between 2 means. You can look at the differences between proportions. You can look at the differences between standard deviations. It is possible, for instance, to have, in fact, some of the stuff I showed you earlier in the semester, where I showed you 3 distributions. All 3 distributions, these were on survey answers. All 3 distributions had the same means, but they had very different standard deviations for them. It is possible to do statistics that compare the standard deviations between 2 different samples. One of the questions that comes, again, inferential statistics can get fairly complex. I had a 3-credit graduate level course, Introduction to Inferential Statistics. And then I had another 3-credit course called Analysis of Variance, which started looking at different ways of doing inferential statistics. And that, and it goes on and on and on. We're not going to get anywhere close to that complexity. But again, I want you to have a sense of, we're going to talk in this class right now about estimation, which is a type of inferential statistics. And the theory behind it is fairly similar. We do estimation when we have data measures from a sample, and we wish to infer the same measures from to the population, and not from. To the population from which the sample is drawn. Suppose, for instance, now I say, suppose I have age and gender data for this class. I do not, actually, but suppose I did. And the measures of the data, the average age of people in this class is 26.4, which is interval or ratio data, as it was standard deviation of 5.3 years. The gender is 65% female, which is dichotomous nominal data. We can ignore this one here. I don't really want to do this, the average height I might have had. And we have 15 people. That's not exactly true, but close enough. Suppose I have that data and someone casually asks me, so what are NVU students like? Well, I've got some data here. I could answer that question for them. But I want to point out this, if I have that information from you folks in this class, that's a convenience thing. That's not That's not a random sample. The number of the people in this class are not a random sample of NVU students. That I would have data from you would makes it a convenient sample. However, it's a low stakes situation. And by low stakes, what other things I mean is, I meet somebody at part of these, and I tell them I teach for NVU, or teach, and they say, "Oh, what are NVU students like?" I'm not trying to get this information published. I'm just, they want some information. I can tell them some information. I am most likely to give simple point estimates and note that online students tend to be older than on-campus students. One of the things I want to do is this is when I start getting the caveats. It's not the most accurate. And one of the real questions comes up is, I believe NVU online students tend to be older than NVU on-campus students. Those are residential on campus. I suspect that NVU online students are younger than NVU graduate students. So there's different populations. There's different populations you might be inferring to in this process. If I'm just sitting and talk with somebody over cocktails at a party or something, oh, NVU students, like, I'm not going to get into all that stuff. I'm going to say, oh, they're about 26 years old, give or take 5 years, and most of them, 2 out of 3 of them are female. Those are point estimates. A point estimate, the best point estimate for the mean of a population, say the proportion or for the proportion or the mean of the population, is the sample mean of a proportion. I do a sample, and you want a quick and dirty estimate. You take just what the sample says. Sample says 26.4. I would say, yep, the average age is about 26.4. And it's about 2 out of 3 are female. Quick and dirty. Low stakes stuff. Doesn't really matter a whole lot. If I'm wrong, it's like, what's going to happen? The person's going to put something in the paper that, oh, the faculty member gave me bad information. No. It's like, it's in some settings, if you are having to do stuff quick and you want to keep stuff simple, a point estimate is absolutely the best way of going. And the best point estimate is whatever your sample is. That's the point estimate. Here I want to note also about, in this week's materials, I have a short one-pager about an article, a case that was going to the Supreme Court. The issue has been that if the Supreme Court says if someone is of low intelligence, that they are at the definition for mental retardation at the point this was put out, that meant if they had an IQ of 70 or less, they could not be executed for a crime, because there was a question about, did they in fact understand the severity or the seriousness of the crime they committed. Now, that's an interesting issue. It is the person I'm having a drink with and talking about NVU students at a party, that's low stakes. This is high stakes stuff. If your IQ comes up 71, you're not retarded by their thing. You don't meet that definition of mental retardation, and you can be executed. If your IQ is 69, you are considered mentally retarded, mentally deficient, whatever it was at the time of this came out, it was mental retardation, the word. At IQ of 69, you are, and you can't be executed. That's pretty high stakes stuff. Now, here's the problem is, an interval estimate is a place where we start getting more, in the article it talks about a person who was, the case came up that they had an IQ of 71. They're over the line. The point estimate is over the line of 70. So they're eligible to be executed for a crime. interval estimate uses the sample mean or the sample proportion and notes the interval that the true mean or proportion is 95% likely to be within. Because the truth is, if you go back and take an IQ test a second time, you may not score exactly 71. You might score 70 the next time, or you might score 72 the next time. There's always going to be some variation. Not a lot, but some variation. The test they talk about here is the Wechsler Adult Intelligence Scale, and it has a standard error of 2.5 points. So point estimate of 75 translates to a 95% confidence interval of 66 to 76. Because 95% is actually, I have it down to 2 here, but it's 1.96 z-scores, 1.96 standard deviations around that point estimate of the mean. What that means, someone scores 71, this person did. We don't know what this true intelligence is. We know the interval that it which is true. It's 95% likely it's between 66 and 76. You give them a second score, 95% of the time it's going to fall in that interval again. You give it again, and 95% of the time it's going to fall with that interval. Occasionally it'll fall further out, but 95%, this accounts for 95% of the case. What it also means is 34 plus 13 is 47, almost 48% of the cases are lower than 71. There's a 48% chance that the person who scores 71 actually has an IQ lower than that, down to like 66. Now, if I'm a lawyer and my client is the one who has an IQ of 71, I want to talk about this because we don't know for sure what the true IQ is. The WACE in every IQ test isn't just WACE, every IQ test has some natural variation. You take a test today, you take it again tomorrow, you're not going to get exactly the same score. You'll get something probably, in this case, you probably get two chances out of 3, you'd get something within between 68 and 73, 68 and 74. 2 chances out of 3 would fall in it. But there's a 48% chance that would fall lower. So chance that we don't know what this person's true IQ is, but there's a 48%, almost a half, 50%, almost a flip of a coin, if you will, that it'll come up lower and cross the line. That's taking into account natural variation. Now, look, judges and lawyers, they get crazy with this kind of stuff, saying, just give me a straight answer. What's the guy's IQ? And the simple answer is, guy's IQ is 71, a point estimate. The more honest, accurate answer is, we don't know what his real IQ is, but we know there's a 95% chance between 66 and 76. That's where his IQ is. And now if you're a judge, say, don't bandy words with me. Tell me, just give me the straight answer. Like, for a statistician, that's a straight answer. That's taking into account what I know about natural variation in any sort of estimate process. That's why this stuff's important. Because when we do tests or when we do any sort of estimate of something, there's always some variation. And how much variation? Now, let me come back. The standard deviation is sigma divided by the square root of n. Now, it turns out for like the WACE, the square n is a pretty big number. That test has been given a lot, thousands and thousands, hundreds of thousands of people probably. So, and you get sigma. How do you know what sigma is? If sigma is the population standard deviation, how do we know what that is? We know what the sample standard deviation is. What? And what if you don't know what the population standard deviation is? Well, actually, there's an answer to that. This gets into, so what test do you use? There are basically two tests that we use. And one is the normal Z test. That thing we saw in the, not last week's, but the week before that, the standard normal deviation, standard normal curve, the Z test. And you get, for proportion, you use Z. And you get the assumed proportion, the difference in proportions divided by the square root of PQ. Well, I'm going to show you an easy way to do this. But let me talk about the mean. The other one that goes on is when you do not know sigma and n is greater than 30, use what's called a t test. Because in most situations, we don't know what the population standard deviation is. In fact, it's a relatively rare case where we know the population standard deviation is. If you know it, then you use a z test for differences in means. If you don't know it, then you use the t-test for differences in means. And just let me note for here, t is equal to the mean, the sample mean, minus the population mean, divided by the sample standard deviation divided by the square root of n. Now it's assuming, then this, what we're doing is we're testing here, is my sample different from what my population is? Now, how do you know what how do you know what the population mean is? Well, we have, in some cases, we have a lot of tests. Some things have been tested so often and the answers come up so consistently that you're going to go on, this is what we use as the population mean. And in some cases, you have that for standard deviation, and in most cases, quite frankly, in most cases, you do not. Sometimes the population mean is what your target is for something. The target is that you have 12 parts per million. I take a sample, and the average of my samples is 14 parts per million. So I have 14 minus 12 divided by the sample standard deviation divided by the square root of n. The standard deviation, this number right here, divided by the standard square root of n, is the standard error of measurement. Down here you have the population standard deviation divided by the square root of n. Again, that's the standard error of measurement. When you know that, when you know sigma, then you use z. If you don't know sigma, then you use the sample standard deviation of that form for the process, and use a t-distribution. The t-test is known as a student t-test. It's not like it's a student version. It's that the person who originally developed it used a pseudonym for the stuff he proposed because he worked, I believe it was for Heineken in terms of doing samples of beer or certain characteristics of samples of beer. And he couldn't use his real name. So he used a pseudonym of student for all the stuff that came out. And so the distribution that he developed that became known as the student T. So I will give you some problems. And when I give you problems, one of the questions you're going to do first is say, wait, am I looking at a proportion or am I looking at a mean? If I'm looking at a proportion, then I'm going to use a z-test. If I'm looking at means, the next question you're going to ask yourself is, do I know sigma or do I not? And if I don't know sigma, then you use a t-test. If I do know sigma, then I use a z-test. That's that's how you make choices about these things. And I can tell you, the problems I will give you will. This is exactly the way you should go at them and stop and say, am I comparing proportions or am I comparing means? And after proportions, I use a z-test. It's means I use, I guess, do I know sigma? And if I don't know sigma, I use a t. If I do know sigma, I use a z-test. Now, let me tell you, I'm going to help make this simpler for you. Because one of the things I do is I include, oh, let me go someplace else here. I include some worksheets like this. And what you end up doing, for instance, is suppose you got a problem. I got an example here. Your sample size is, first of all, let me just note for you here. You own these worksheets. Here's a recommendation. Open the worksheet, save it. Open it a second time, save it under a new name, and then work with the second one. So if you screw it up, you can go back to the original and have it available to you. You only put values in the green areas. Sample size, for instance, suppose I look at this one here and say my sample size is 1,000. Proportion that have the trait is 0.44. And I want an alpha of 0.05. Bingo. And what it says to me is 95% of the cases will fall in the range of between 0.41 and 0.47. That gives you a confidence. That's the confidence. It just jumps out at you. And by the way, the margin of error, which is also the standard error of measurement here, is 0.03. If you look at 0.44 plus, this must be rounded off here to 2 decimal places, but plus or minus 0.03. Now, if I save this, I have to come back. By the way, if you change around any of the, if you change anything in the what's red here, you'll get yourself in trouble. Simpler to do it just this way. Let me come back. A z confidence interval for a z distribution. Suppose when a z-test is appropriate, again, only put stuff in places here where it's not red because your values will show up down here. Suppose I want an alpha of 0.01 instead of 0.05, and my mean is let's use the 26.5 for the age thing I talked about here, and the population standard deviation. And I have to have population standard deviation here, not which I'm going to say is 4.3, and my sample size is 44. What that says is, okay, the confidence interval, 99, well, my mean was 26.5. The confidence interval is 96 or 99% of the cases will fall between 24.8 and 28.1. It gives you confidence intervals right away on things. That's how you use the, I mean, by the way, there are z-tests and t-tests in the Excel formulas. I can pull that up here. T distribution, two-tailed T distribution, right-hand tail, t-test, z-test, let's pull up z-test. And I mean, you got to put stuff in here. And I got to say, you've written your range of data in here. I don't find that useful. And well, if you're doing more sophisticated z-tests, that would be helpful. For what you're going to have to do in this class, use my worksheets. They're the simplest way of doing it. You can try and use the formulas if you want to, because they're in the chapter. My recommendation is use what I have, what I provide you here, because it'll make your life simpler, and it keeps the issues more straightforward to you. So that's the brief introduction to estimation and sampling distributions. Have a sample, you have statistics for the sample, means, X bar, and SD. For the population that you're trying to infer to, you have parameters, mu and sigma. The idea is, and then you have a thing called the standard error of measurement, and that's equal to standard deviation, either standard deviation or sigma over the divided by the square root of n. And that tells you how much variation would tend to go on for that size, for the size of sample that you have. And what you're trying to do is infer from your sample to a population. I know this about my sample. I'm trying to infer to this population about this. Now you can infer means. You can infer about differences in proportions. You could do inferences about standard deviation or variance. That gets into F-tests and all stuff, which we're not going to do here. I'm going to keep it to means and standard deviation, means and proportions. Those are the two simple ones to do. And how to go from a sample and infer that to the population. And one of the things that can happen with that is if I know what some of the population, for instance, if I know what the population mean is, and I know what my sample mean is, and I know what the population standard deviation is, I can tell, is my sample unusual compared to the population? Is there something special about the sample? I showed you a standard normal distribution, middle part black. What you end up doing for trying to figure out whether a sample is significantly different, statistically significantly different from a population, is you compare those differences. And you're looking at, instead of the central part, you're looking at, do they fall outside of it? For instance, if I know the population mean and the population standard deviation, I can go back and put it in that z-test I gave you. And it would say, okay, the 95% of the cases fall between these two things. But my mean falls up here, outside that boundary. So that means it's statistically unusual. That means the same thing as statistically significant. It could be below it, could be above it. If it's outside that boundary, that confidence in it, then it's significantly different. And there's something about it. I can look at the proportion, and there's a problem going to come up here. I can look at my proportion of my population that has bald heads. And I can look at my sample, what percent of my population, my sample population is bald. And I can look to say, oh, it comes up 45%. What's the population percentage proportion that has baldness? And maybe it comes up 40% as opposed to 45. And then I can say, so what's the 90, because I know sigma, or even if I don't know sigma, I know what the standard deviation is in my sample. I can find out what's the confidence interval around the population proportion, and say, is my proportion bigger than that, or is it less than that? If it's bigger, then it's statistically significant at whatever your alpha level is. 0.01, 0.05, 0.001, whatever you set it at here. 0.01 and 0.05 are those common. So that's what we're going to talk about this week. Feel free to ask questions. This is complex. I appreciate that. Articulating a question can be useful in understanding what you know or don't know. And I encourage you to ask questions this week. Next week is the final exam. And I'll say more about that tomorrow. That's it.